In this episode, we build a clear, beginner-friendly picture of how application security testing fits into modern software delivery, and why a strategy matters more than any single test. People new to this area often hear a pile of acronyms and assume security testing is a magic scanner that finds all problems automatically. But in reality, each type of testing sees different things, misses different things, and produces different kinds of results. A strategy is the plan for combining those strengths in a way that improves security without overwhelming teams or slowing delivery into frustration. The title includes static application security testing, SAST, dynamic application security testing, DAST, software composition analysis, SCA, and triage. And those pieces belong together because triage is what turns raw findings into decisions and action. If you skip triage, you get noise and theater, where the organization generates findings but does not reduce risk. If you skip a balanced mix of testing types, you get blind spots, where the system looks tested but still fails in predictable ways. The goal here is not to teach you tool operation, but to teach you how to think about what each testing approach can and cannot do, how to sequence them in the delivery lifecycle, and how to handle results so teams build safer software over time. A good starting point is to understand why we need multiple testing approaches at all, because beginners often expect one perfect test to exist. Applications are complex systems with code, configuration, dependencies, and runtime behavior, and security problems can live in any of those places. Some problems are visible in source code patterns, like unsafe handling of input or missing access checks in logic. Some problems are visible only when the application runs, like how it responds to unexpected requests or how it exposes errors. Some problems come from dependencies you did not write, such as vulnerable libraries. Because these problem types are different, the tests that find them must also be different, and that is why SAST, DAST, and SCA exist as distinct categories. Another reason multiple tests are needed is that development is a process over time. So the most useful feedback is the feedback that arrives when it is cheapest to act on. A strategy recognizes that different tests fit better at different moments, and it plans for that fit. Beginners should see that the purpose of security testing is not to prove perfection, but to reduce risk by finding issues early, by preventing repeat mistakes, and by providing evidence that controls are working. Static application security testing, or SAST, focuses on analyzing code without running the application, which means it is oriented around patterns and structure rather than runtime behavior. For a beginner, the simplest way to understand SAST is that it looks for code constructs and flows that are often associated with vulnerabilities, such as unsafe use of untrusted input or risky patterns in authentication and authorization logic. Because it works on code, SAST can be applied early, even before a feature is fully integrated or deployed, which makes it valuable for fast feedback. It can also scan large code bases consistently, which helps catch repeated patterns across teams. At the same time, SAST has limitations that beginners should understand clearly, because it can generate false positives, meaning it flags something that looks risky but is actually safe in context. It can also miss issues that depend on runtime configuration, external systems, or behaviors that only occur when the application is running. Another challenge is that SAST results can be overwhelming if the strategy is not thoughtful, because a raw scan can produce a long list of findings that teams cannot realistically address at once. A good strategy therefore defines how SAST is used, where it is focused, and how results are prioritized so it supports progress instead of creating a backlog nobody trusts. Dynamic application security testing, or SAST's complement, is dynamic application security testing, DAST, which evaluates the application while it is running. The beginner-friendly view of DAST is that it interacts with the application like an external user or attacker might, sending requests and observing responses to see whether the application behaves securely under stress and unexpected input. Because it observes real runtime behavior, DAST can find issues that are hard to spot from code alone, such as misconfigurations, improper error handling, or unexpected exposure of functionality. It also helps validate how the application behaves in an environment that resembles reality, which can reveal gaps between design intent and deployed behavior. However, DAST also has limitations, because it cannot easily see deep internal logic unless that logic is exposed through reachable paths. If a vulnerable path is not exercised during testing, DAST may not find it. It can also struggle with complex authentication flows and user states if the test approach is not designed to cover them, which is why strategy matters. Another important point is that DAST tends to happen later than SAST because the application must be runnable, which means fixes might be more disruptive if they are discovered very late. A balanced strategy uses DAST to validate and discover runtime issues while still relying on earlier checks to reduce the chance of late surprises. Software composition analysis is the third key category, and it focuses on dependencies and components rather than on custom code. Beginners should remember that most modern applications include many libraries, frameworks, and modules, and vulnerabilities in those dependencies can become vulnerabilities in the application, even if the application code is clean. SCA is about identifying what components are in use and evaluating whether those components have known issues or risky characteristics, such as being unmaintained or having a problematic version history. The value of SCA is speed of response, because when a new vulnerability is discovered in a widely used component, teams need to know quickly whether they are affected. SCA also supports better decision-making during development, because it can guide teams towards safer versions and away from risky choices early. The limitations include the fact that SCA is heavily dependent on knowing what is actually included, which can be complicated by indirect dependencies and build behaviors. Another limitation is that not every component issue is equally relevant, because a vulnerable component might not be reachable in your application's actual usage. This is where triage becomes critical, because it helps teams decide whether a finding represents real risk or theoretical exposure. A good strategy treats SCA as part of supply chain discipline, not as an optional scan, and it connects component findings to remediation plans that fit delivery schedules. Now that you understand the three testing categories, the strategy question becomes how to combine them in a way that creates high-quality feedback instead of chaos. A beginner might think the best strategy is to run everything all the time, but that often backfires because it creates noise and slows delivery without improving outcomes. A smarter approach is to align each testing type to the moment where it is most useful. SAST is strongest earlier, when code is being written and reviewed, because it can catch risky patterns before they spread. SCA is useful continuously, because dependencies are introduced, updated, and sometimes become vulnerable due to new discoveries, so component risk changes over time. DAST is strongest when an application build can be run in a realistic environment, because it can validate runtime behavior and catch misconfigurations. The key is to design a pipeline where early checks prevent obvious mistakes, midstream checks confirm component choices, and later checks validate real behavior. Beginners should see that this reduces rework because the most avoidable issues are caught early. It also makes DAST results more meaningful because the baseline quality is higher, so runtime testing is not flooded by basic errors that should have been prevented. Strategy is therefore about sequencing and focus, not just about running scans. Triage is the part that makes the strategy operational, because triage is how you turn findings into actions with the right urgency. Triage means sorting findings by risk and reality, deciding what is truly important, what is likely false, what is already mitigated, and what needs immediate attention. Without triage, teams drown, and when teams drown, they either ignore results or they waste time fixing low-value issues while high-value issues remain. A strong triage approach considers impact, likelihood, and exposure, meaning how much harm could occur, how plausible the exploit is, and whether the vulnerable behavior is reachable in the real system. For example, a dependency vulnerability might sound severe, but if the vulnerable functionality is not used or not exposed, the immediate risk might be lower, though it still deserves a plan. Conversely, a seemingly minor issue in an authentication workflow might be high impact because it affects the core trust of the application. Beginners should recognize that triage is not about minimizing work by dismissing findings. It is about allocating effort intelligently. Triage also builds trust in the testing program because teams learn that when an issue is marked as urgent, it truly matters. This trust is what keeps security testing from becoming an ignored background noise. A common beginner misunderstanding is that triage is purely a security job, but in practice, triage often requires collaboration because understanding reachability and context depends on how the application is built and deployed. Developers can explain whether a code path is used, whether a library feature is enabled, or whether a finding represents a real workflow. Security specialists can explain threat likelihood and potential impact patterns. Operations teams can explain deployment realities, such as whether a feature is exposed publicly or restricted internally. Shared ownership improves triage quality because the decision is grounded in reality rather than in assumptions. This also helps avoid conflict, because when triage decisions are made collaboratively, teams feel the process is fair and informed. Beginners should see that triage is also a learning mechanism, because recurring findings can reveal deeper process problems, such as unclear secure coding expectations or risky dependency habits. When triage is documented well, it becomes a record of reasoning that future teams can learn from, preventing repeated debates about the same issues. Over time, triage outcomes can guide tuning of SAST and DAST rules so the signal improves. This is how the strategy becomes better, not just bigger. Another essential part of the strategy is managing false positives and noise without accidentally missing real issues. All scanning approaches can generate findings that are not meaningful in context, and if those are not handled thoughtfully, teams lose confidence. The wrong response is to turn off testing when it becomes annoying, because that creates blind spots. The better response is to tune the approach and to set thresholds that match risk. For example, early SAST feedback can be used as guidance rather than as a release blocker until teams are ready, while certain high-impact patterns can be treated as must-fix because they represent unacceptable risk. Similarly, DAST findings can be prioritized based on whether they affect exposed endpoints or sensitive workflows, rather than treating every unusual response as equally urgent. SCA findings can be triaged based on whether the vulnerable component is reachable and whether an update path exists. Beginners should notice that tuning is not cheating. It is the act of improving fidelity, so the program focuses attention on what matters. Noise reduction also improves delivery speed because teams spend less time chasing low-value findings. A good strategy makes noise visible and then reduces it systematically, which is a sign of maturity. Strategy also needs to address timing and cadence, because security testing is not a one-time event, but a continuous practice that must fit into release rhythms. If your release rhythm is fast, you need fast feedback loops and clear prioritization, because slow reports that arrive after release are less useful. If your release rhythm is slower, you still need periodic checks because dependency risk changes even when your code does not. Beginners should understand that a vulnerability can become relevant without any code change if a new issue is discovered in a component you already use. This is why SCA and continuous monitoring of components are important as a baseline. For SAST and DAST, cadence decisions should reflect risk, such as running deeper tests on major releases or on changes that affect sensitive data flows. The key is to avoid treating security testing as an afterthought that happens only when someone remembers. When testing is integrated into the normal process, it becomes predictable, and predictability reduces friction. Predictability also supports shared ownership because teams can plan around the checks rather than being surprised late. A strategy that matches cadence makes security sustainable, which is the real goal. Finally, it helps to connect the testing strategy back to the broader goal of building better software, not just finding problems. Findings should feed improvements in secure coding expectations, design practices, dependency management, and operational guardrails. If the same pattern appears repeatedly in SAST, that is a signal that developers need clearer guidance or safer reusable components. If DAST repeatedly finds misconfigurations, that is a signal that environment setup needs better guardrails and review. If SCA repeatedly flags risky components, that is a signal that dependency selection and updating practices need attention. Beginners should see that the testing strategy is not separate from DEVS ECOPS adoption. It is one of the ways adoption becomes measurable and real. Testing provides evidence. Triage turns evidence into decisions, and those decisions drive improvements that reduce future risk. When this loop is working, the number of urgent surprises should decline, and the organization should become faster at responding when new issues appear. That is the ultimate purpose of a testing strategy, to make security improvements steady and practical rather than chaotic and reactive. When you step back, building an application security testing strategy is about combining SAST, DAST, and SCA in a way that covers different risk areas while keeping results actionable through disciplined triage. SAST helps find risky code patterns early. DAST validates real runtime behavior and catches issues that code scanning cannot see. And SCA manages the risk you inherit from dependencies and components. Strategy is about sequencing these approaches to fit the delivery lifecycle and about tuning them to reduce noise while still catching high-impact issues. Triage is the heart of the system because it converts findings into prioritized actions based on impact, likelihood, and exposure, and it builds trust that the program is focused on real risk. Shared ownership improves triage and remediation because context comes from multiple teams, and the best decisions are grounded in how the application actually works. For a beginner, the most important takeaway is that security testing is not a single scanner and not a one-time step, but a coordinated feedback system that helps teams ship safer software repeatedly. When you build that system thoughtfully, you reduce late surprises, improve confidence in releases, and make security a normal part of delivery rather than an emergency at the end.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.